Got Travis here. Where's Travis? There you go. You get to do the first dot product. So I'm going to go V dot U. And so like give me like what I need to write down now.
So you write the bracket or the curve?
Do not need it. Because remember the answer is going to be a number, right? So you're just going to start listing out things here.
Okay, so that would be 2
Times negative 3. And do it like that. Plus
negative 3 times 4.
negative 3 times 4. I'll do it like that.
5 times 7.
5 times 7. There we go. Like that. And then we just calculate all that. Negative 6, negative 12, negative 18, 35, right? Something like that. What is it? 17? I can't do arithmetic.
17.
17, that's what I thought. Okay, 17. Yay. What does that tell you? Right? It's like you have 2 dogs and there's a mouse, right? What the hell happened? Okay, so we get 17. That's how you do it. Mechanically, it's pretty straightforward, right? Mechanically, computing a dot product, there's no magic to it, as long as you can do arithmetic. Oh, by the way, this is going to come up in a second. We're going to actually show some of the properties, but let's just think about this for a second. Would it be any different had we done u dot v instead of v dot u? Oh shit, I wrote it down wrong. Well, I did v dot u here, didn't I? I did that dot with that, but would it be any different if I did it the other way? I wrote it down. We should have done that, but does it matter?
Different.
Do we get the same answer or not?
No, yes. No, you do get the same answer.
You do get the same answer, because now I'm just going to go this times this, right? Plus this times this. So all it would do is flip the order of, it would flip the order of the multiplication, wouldn't it? It would flip the order of the multiplication, but that doesn't change anything, because we know multiplication does flip. That's called commutative property. Not commutative, commutative property of multiplication, that it doesn't matter the order. So it turns out that the dot product is commutative also. Dot product doesn't matter, the order doesn't matter how you do them, all right? But I'm sure you're just sitting there on the edge of your seat like wanting to know what it means, right? And I'm still not going to tell you. Here are the properties, here are some properties of dot products. All right, first property of a dot product is that if you dot a vector with itself, then you're going to get right, u1 dotted or multiplied plus u2 plus u3 and I say that that's the magnitude of u squared. Do you agree with that? If I gave you a vector u and I said it was the vector u1, u2, u3, if I gave you that vector and asked you for its magnitude, what would you tell me its magnitude is? Magnitude. How long is that vector?
u1 squared plus u2 squared.
Yep, square root of u1 squared plus u2 squared plus u3 squared, right? That's what the magnitude would be. But if we do the dot product, u dotted with itself, don't we get u1 squared plus u2 squared plus u3 squared? Don't we? But see, this one's sitting under a root. That one's not. So if I square both sides, then that is u dot u, isn't it? So there's this really nice property that if you dot 2 vectors to get, sorry, not 2 vectors, if you dot a vector with itself, it has to be itself, then it's equivalent to the length of the vector squared. This is what I told you a second ago. You can flip the order of a dot product and it has no effect on the answer. Commutative. The dot product is also distributive over addition, meaning if we have 2 vectors being added and we want to dot that, then what you can do is it's almost like you can dot this vector plus and then dot that vector separately. This result would be the same as that result. These are all in your book and don't need to necessarily be memorized. Just know that they exist. This one has to do with scalars. You scale a vector, then dot it with another vector. Well, you don't have to scale it. You can dot them first, then scale. Or you can even move the scalar to the other vector. So this is the way things can be, the way that C can be moved around with dot products. And the last property, I think it's the last property, yeah, that the zero vector dotted with any vector is 0, the number 0. We'll skip that. Now here's the big, this is the big daddy right here. This is the big theorem, all right? For this section, this is the big theorem. The dot product theorem. If theta is the angle between two vectors, u and v, then the following is true. The dot product, right, which we set as a number, is equal to the magnitude of u times, since there's no symbol there, this is times because magnitude of u is a number, isn't it? Magnitude of v is a number. So these are two numbers multiplied times cosine of theta. Now I'm not going to prove this theorem in here, but if you're interested in knowing where it comes from, you can come to my office and we can go through the proof. So that means that the dot product is the product of the lengths of the vectors times cosine of the angle between them. So what? Who cares? What's the big result of this theorem? So I'm going to put the theorem right here. U dot v equals magnitude of u times magnitude of v cosine of the angle between them. So here's what's so important. Let's say you have two vectors, right? And the angle between them, or I'm saying if someone gives you two vectors, the angle between them must be between 0 and pi. So this is where things get a little bit weird. Let's say I have two vectors. These vectors do not have the same length, right? So they're different already. Let's say I take this vector, and let's say two-dimensional space. These vectors, if I put them tail to tail, not tip to tail, like we're adding them, tail to tail. So this one's pointed in that direction, this one's pointed in that direction, tail to tail here. Then do we all agree that there is an angle between them, right here? Now when we say angle between them, we're always talking about the smallest angle, because you could argue that there's an angle between them this way too. But we're talking about the smallest angle between them. And no matter what, as long as these are non-zero vectors, there's some angle between them, and the limit on that angle is 0 to pi. So 0 would be they're exactly pointing in the same direction. Pi would be they're exactly opposite, right? But once I go past that, then now you'd be looking at the angle down here, right? I don't have three, I really need 3 hands. There we go. So as soon as we go past pi, right there, then if you go past it, now you're talking about that angle. And that's between 0 and pi. So do you all agree that the smallest angle between two vectors has to be between 0 and pi? Yes? Okay, now we can proceed. Now think about the cosine function in pre-cal. If we take the cosine function and we restrict it to the interval 0 pi, here's 2 pi, here's pi. Cosine looks like this. Right, that's what cosine looks like. So we're not looking over here, right? We're looking just at this, between 0 and pi. If we restrict ourselves, we know that when theta is 0, when the angle is 0, cosine of that is 1, right? So that would mean that if the angle between them is 0, that means they're pointed in the same direction, right? Both vectors are pointed in the same direction. That when we compute the dot product, we're going to have cosine of 0 here, and that's 1. And so it's just the lengths of the two vectors multiplied together, right? So in the event that you have two vectors pointed in the same direction, the dot product represents the two lengths of the vectors multiplied together. That's what it is. This is not very useful, all right? This one's not, okay? Now, what if theta is pi over 2? Pi over 2 is here, right? Cosine of pi over 2 is 0, and that's the big one. Because if the angle between the two vectors is pi over 2, then that means the angle between them is a right angle, yes? That means these vectors are perpendicular. And the dot product would have to be what if they're perpendicular? 0. Because cosine is going to be 0. So if the two vectors are 90 degrees between them, then when we compute the dot product, we are going to get 0 as an answer. And this is actually how we are going to check to see if two vectors are perpendicular. We will check by seeing if the dot product is 0. See, I have just a couple of exclamation points there. Okay? This means that if the dot product between two vectors is 0, we can say the vectors are perpendicular. Now, another word for perpendicular is the word orthogonal. You will hear me say that. If I say orthogonal, I mean perpendicular. So I have a theorem coming here. Now, I could read through the rest of that, but I think I can do this visually. Yeah, here it is. Okay, you see these two vectors? You see the angle between them, right here? That angle is between 0 and pi over 2, right? And therefore, cosine between 0 and pi over 2 is positive, right? Any number here, any angle here, we're going to get a positive number, aren't we? So when we do a dot product, it should be the magnitude of u times the magnitude of v, which are both positive numbers, times cosine of an angle, and that will be positive, right? So long as we are between 0 and pi over 2, the dot product should be a positive number. See it up there? It's positive. Now, as I make this angle grow, just keep an eye on the dot product. Here it is. As I make this angle grow, it's still positive, right? But what is it getting closer to? 0, because you're about to be orthogonal. You're about to be perpendicular. There, I got it. Okay. I say positive here. It's just my code, sorry, had a problem. Doesn't know what to do right now. So right now, the dot product is 0 because they are orthogonal. Once I go past pi over 2, right? Now we're in here. And so cosine, that should give you a negative number. So look at my dot product. It's now negative. We have an obtuse angle. So if we compute a dot product, didn't we do one a second ago? We did one together, didn't we? Where is it? No. We did that, didn't we? And what did we get as our answer? 17? 17. What can you tell me about those two vectors? The angle between them is what? Somewhere between 0 and pi over 2. That's what you can tell me. The angle between them is acute. That's about all you can tell me, but that's pretty good, right? No? Still not happy about that? It'd be nice if you could just find the angle, right? Oh, but you can. This one's almost trivial. This example. I give you two vectors. I tell you their lengths, and the angle between them, ask you to find the dot product. So all you'd have to do this is what? 7 times 3 times cosine of 31 degrees. And you want to make sure your calculator is in degree mode if you did this. Compute that, you're going to get the dot product. Okay? Are these two vectors orthogonal? Are these two vectors perpendicular?
No.
No, why not?
The angle between them was 31 degrees.
These two? No, sorry, we switched over. I moved on, sorry. You were calculating. Are those two orthogonal? Rose? Are those two orthogonal? Hold on. We're gonna let Rose think through this. So, if you're gonna take anything away from this section, Rose, and everybody here, it's that the dot product is a test, is something you can use to check for orthogonality, to whether or not you are orthogonal or perpendicular.
So I'm working.
Just do a dot product right now. Just dot product that.
So dot product for this would be the 2 times 6.
Yep.
Right?
Yep.
Plus 4 times -3.
Right?
And then after this, don't I have to do the dot product theorem? Or just
Nope. What is, well, yes, but what is this equal to?
Oh,
0. And the theorem tells us, or we know, that if the dot product of two vectors is 0, they're orthogonal. Now, if this would have turned out to be 4, you would have said, no, they're not orthogonal. So the answer is yes. Okay, yes, these are orthogonal. That's a pretty easy way to check, huh? I like that. Okay, so this one's different. This is a little different. I give you a vector u. I tell you it's 2, negative 2, 6. I give you a vector v. I tell you it's a, 3a, negative 2a. Find the a such that these two are orthogonal vectors. I want you to tell me what a would have to be in order for these two to be orthogonal. So it's like somebody's given me a vector, and I'm trying to find another vector that looks like this, just a has to be determined. So what do? What do I want to happen? I want what? I want the dot product to be 0, don't I? That's what I want? Okay, what is the dot product of those two vectors? 2a plus or minus 6a. And you know what? I remember this problem. This is a really boring problem. Can we just scratch out that a? Just make that negative 2? Because it's a really stupid problem after, because you get a is 0 and then it makes it the 0 vector and it's kind of dumb. But okay, that's that. What's the last piece? Minus 12. If I take that a out, I need that to be 0, right? Okay, so in that case, now it works out a little bit nicer. I can solve for a here. So negative 4a minus 12 equals 0. And so at the end, you get a is negative 3. A is negative 3. So now if I rewrite this vector, I get negative 3, negative 9, and negative 2. So just replacing a here with what we got. This vector should be orthogonal to that vector. There's one like this on your take-home. There is. But when you do this, you're not going to get a linear equation. You're going to get, I believe, a 4th or 5th degree polynomial. Yes?
So is the 0 vector perpendicular?
You could say that the 0 vector is orthogonal to every vector, which is weird, right?
Yeah.
It's orthogonal to everything. But usually when we talk about orthogonality and being perpendicular, we say, let's not talk about the 0 vector. Because it doesn't have direction. So it's like orthogonal to everything, but orthogonal to nothing. It gets weird. Okay, so on your take-home, you're going to have like a 4th or 5th degree polynomial that needs to be solved without a computer. And the reason why I give you that problem is because I want to see if you're going to go get help. You might need help. And it's going to be something from college algebra. You may or may not have seen it. It's how to solve polynomial equations of higher degrees. And there's usually a set of steps. It works out real clean if you know how to do it. But if you don't know how to do it, you're going to be stuck. So, you know, I told you you can work together. I told you can ask for help. Further results of this beautiful formula. If somebody gives us two vectors that are non-zero vectors, and we would like to know the exact angle between them, then there's a formula for it, right there. And that formula may look crazy, like where did it come from, but it's just the same thing we just had. If I wanted to solve this for theta, the first thing I would do is divide these two on this side, right? So I'd divide by magnitude of u, divide by magnitude of v. So if I do that, magnitude of u, magnitude of v, divide those through on both sides, then I would have cosine theta on the right-hand side, wouldn't I? And then to get theta out of the cosine, I do arc cosine here, arc cosine here. When I do arc cosine here, I get this formula, and I do arc cosine here, it kills off the cosine, we get theta. So that's just the theorem solved for theta. This formula gives us a way of finding the angle between two vectors. As long as they're non-zero vectors, this works, right? Find the angle between these two. You ready? Find the angle between these two. Cameron, where's Cameron? Cameron? Bueller? That's a bad joke, but Cameron is in Ferris Bueller. It's his best friend, right? Was it a bad joke?
I'm just kidding.
But Cameron is Bueller's friend. Right? Still bad? Fernando. Where you at, Fernando? Right there? Okay. I would like us to find the angle between these two vectors. All right? Now, there's something, Fernando, that I want you to consider. It's kind of strange, but remember we have two vectors, right? One of them, it's in three-dimensional space. One of them's like pointed out here, and one of them's like over here doing whatever, right? There they are. They have length and direction. When I'm trying to find the angle between them, I need to attach them tail to tail. So that means I can move this up, down, left, right, move this one up, down, left, right, doesn't change it, right? So I just kind of, move them and I bring them together like this, okay? The angle I'm talking about is, imagine if I kind of twist it, just so you can see this. You see that like plane that goes through both those? And then I'm turned like that? I'm talking about that angle right there, okay? Because it's kind of weird, a vector in three-dimensional space, what angle where's our reference point? Like, what do you mean by angle? Because we have 3D. In 2D, it's easy. We just, here's the x-axis, there's the angle we're talking about. So do you kind of see what we're talking about, the angle between these? Okay, do you have a question or do you have an answer?
Yeah, this might be like further along
Okay.
in our lessons, but is there a way of defining a plane of any angle in 3D space?
Defining a plane of any angle?
Yeah,
Like you give me the angle and I define the plane?
Yeah, or like an equation for planes in 3D, or is it like a standard for plane?
Oh yeah.
Okay.
Oh yeah, you could tell me, pardon?
I hate to try, but I'm sorry. You might have shook a little bit.
Yeah, no, I think we're okay. Thank you for letting me know. I've had people like practically knock the damn thing over and not tell me, and then I look at the video later and it's like over there. Okay, that's great. We're good. Yes, later on we will be able to define a plane two different ways. Initially we won't use vectors, but then later on we will use vectors because they're easier to use.
Okay, thank you.
Yeah. All right, so where were we? Cameron wasn't here, bad joke. Fernando, right? Fernando, so you visualize, can you visualize the angle we're talking about? Did that help with the visualization a little bit? Okay, so to compute it, we need to use this formula. So Fernando, what out of that formula do you feel like going after first? Dot product. Okay, so let's do that over here. We're going to do some scratch work. U dot V, can you crank that one out for me? -6 plus 28 plus 4. We all good? Okay, so what's that, 26? All right, good. So we got the numerator. Now, we need magnitude of U and magnitude of V. So those are two computations we got to do again, right, over here. So magnitude of U will be, Fernando, you want to keep going? Or should we let Quentin go? Where's Quentin?
Right here.
All right, look at that. Magnitude of U, we do, oh, I forgot to put magnitude, I'm sorry. Yeah. Yeah, you may not have written the formula down. Let me see if I can help you.
Oh yeah, it's a square root
Square root and then
of all the components.
all the components squared. So
Together, so
4, 16, 16. There you go. 32, 36, 32, 36, right? Which is just 6. Okay, and then we need magnitude of V, right? So same thing, but I'm going to use the V vector now. So 9, 49, and 1, 59, root 59. There we go. We got all the pieces now. And we come over here. Theta is arc cosine of 26 over 6 times root 59. And we grab our trusty calculator. And just be aware of what mode you're in. Let's get the mode in degree mode, because I think if we get a degree answer, it'll make the most sense to us. Did you get something already?
It's 55.65 degrees.
55.65 degrees. Does that sound right to everyone? Anyone else get that? Now, there is one thing I could check just to kind of make me feel better that my answer's right, and that's to be like, this is a positive angle. I mean, sorry, not a positive angle. It is an angle between 0 and 90. So my dot product should be positive, shouldn't it? And that was positive. So this being a positive number and that being an acute angle makes me feel good that I'm probably right. Is that okay? All right. Now, let's see the true power of the dot product. This one right here. I'm giving you the vertices or the corner points of a triangle in three-dimensional space. So imagine in this room that I've given us 3 points in space. Okay? Is that triangle a right triangle? Now, I'm not sure if this is going to, if you would agree with this or not. Maybe you don't understand. That's not the right word. Maybe it's difficult for you to appreciate the difficulty of this problem without a dot product. If I just gave you 3 random points in space, in 2-dimensional space, this wouldn't be too bad. But I'm talking about 3-dimensional space. So maybe I grab this point right here. I grab my tripod camera and I grab like this point right here. And I say connect those 3 points and make a triangle. Is that a right triangle? How are you going to check? You cannot use the Pythagorean identity because you're not flattened down on a sheet of paper. So a squared plus b squared plus c squared does not hold. Does that make sense that it doesn't? So how do you determine that?
Find the lengths of everything and use it for law of cosine.
So maybe we could find the lengths of each side and verify that it qualifies like law of cosines or something like that, right? We could, yeah, that seems totally reasonable to do that. That's one approach. Doesn't involve vectors though. Was there someone else have an idea?
Can you just do the dot product theorem, but with all 3?
We can do dot product, yes, with all 3. What do you mean all 3?
All 3 components. So
Not sure I'm understanding IJK. I think you're correct, but I'm not quite sure it's
yeah.
verbalized.
Clear, I wasn't supposed to use dot product.
You can use dot product, but not IJK.
Oh,
So do we do like A to B is one, thank you, A to B
Okay.
is one vector, and then like B to, or like, and then pick two vectors and do something like that?
Exactly. Okay, so this is the way we want to do this. If this is a right triangle, then one of the angles is 90 degrees, right? Which means, let's say we're focusing our attention on this angle right here, and I'm just going to call it theta. If I take the vector that goes from here to here, and then I create the vector that goes from here to here, and I dot the two, if I get 0, that's 90 degrees, isn't it? If I get something other than 0, what? I move on to the next angle and try again. One of these has to be 90, right? If it's a right triangle. So I check these, I figure out what these vectors are, and then I dot them. It's either yes or no, 90 degrees, right? If it's not, I move on, I'm going to go vector from here to here, here to here. So I'd have to try again with something else. I'd have to do maybe here to here, C to B, and then here to here, C to A, right? So let's do it. I think we can do this. Let's try the first one. What is the vector from A to B? It's a vector, right? What's the vector? You have to change the points to vectors, right? You cannot use these as vectors. These are not vectors. So what is the vector that goes from A to B? 1, 3, 6. So remember, we're going from A to B, right? So you do 2 minus 1, 0 minus negative 3, 4 minus negative 2. That will create the first vector from A to B. Now any questions there? I mean, we did that earlier today, so I realized like this is a lot happening here. Now from A to C, what's that vector? From A to C. Negative 7, 1, negative 3. Now what? Dot them. What's AB dot AC? Negative 7 plus 3 plus negative, or so minus 18. That's not 0, is it? So I move on. I try something else. The thing I've always found just completely fascinating about this is the fact that I'm going to be able to determine if this is a right triangle by just doing addition, subtraction, and multiplication. Like there's no trig functions, nothing, right? If I can add and multiply, I can figure out if this is a right triangle or not. Okay, so let's try something else because that failed. Let's go off my drawing here. How about the vector from C to B? So this is a separate kind of test here now. The vector from C to B. And let's call this angle here beta, just so we have a reference point. Vector from C to B? 8. 2. 9. Okay, check this out. How about the vector from C to A? 7, negative 1. Man, that was quick. How'd you do that?
Just scaled AC by -1.
Yeah, isn't CA, AC flipped over? Yeah. So just change the numbers, right? You don't have to go calculate it again. The vector from here to here is the vector from here to here, just pointing in the opposite direction. Dot them. $56 plus minus 2 plus 27. No go, right? All right, well. We need 2 more vectors, don't we? To test the last one. Let's call this alpha. So to do alpha, I'm going to do two new vectors. Here to here, that's BA. And then here to here down is BC. And the good thing about BA and BC is we already have those vectors. We just need to flip them around, right? So the vector, I'm going to do it right here. The vector BA is the vector -1, -3, -6, right? And the vector CB, no, BC is CB flipped. So this one. -8, -2, -9. And now dot them. Has anyone done it yet?
Still doesn't give you 0.
Okay. So what does it give you?
Gives you
8, 6, 54, something like that? It's not 0. So that's not a right triangle. Yes.
During the first one, finding the angle theta,
Uh-huh.
I realized that -7 is too much 18. Once you go to the negative number.
Wait, start over. Say again.
When we found the first dot product between AB and AC, and -7 plus 2 minus 18, since that gives us a negative answer, doesn't that make it an obtuse angle?
Yes.
So it automatically could have been right triangle.
You could have thrown it out right there, yes.
That's, yeah.
Yeah. That's, yeah, you know what? Yes, but then I wouldn't have been able to show you how you do it. Yes, but that could have been noted in the beginning. If you have an obtuse, then you can't be right if one angle is obtuse. That's a good observation there.
Thank you.
So this is not a right triangle, right? It's not. Oh, well. We have 4 minutes. The sign-in sheet did not go around, so I'm going to need to pass that around real quick. So we're a little behind, okay? We're supposed to do this section and cross product today. We have a little bit more to do here, a lot of bit more, and then we get to the next section. So we'll have to pick up there. I think it's starting to look like perhaps that first take-home might get pushed till next Wednesday. You can do a few of them now, but there's quite a bit you can't do. Are there any questions over anything? Well, I'm not going to start this new part here in the last 4 minutes. Are there any questions over anything?
Yes, sir. Could you explain again what exactly the dot product represents? Like, what is it exactly?
Well, it depends on how you want to perceive it. It is the length of the two vectors multiplied times cosine of the angle between them. Now, that doesn't mean a lot unless the angle between them is something important. If the angle between them is 90 degrees, then you know it's 0, so the dot product, you know, you're going to get 0. So that in itself, I'll tell you right now, that in itself is like enough for us to be happy with the formula, you know? That the dot product being 0 tells you have two orthogonal vectors. But if it's positive, then you know that you've got an acute angle. If it's negative, you've got an obtuse. And that formula actually gives us a way to calculate the angle. Like on that triangle that I just drew, we could have found the angle, but we could have used the dot product formula to find the angle for all three angles for the triangle. We could have.
Okay.
We didn't because it would have been too time consuming.
But that also could have told us that it wasn't like you could have used both ways.
We could have. So we could have looked at that first angle, theta, and we could have found the angle. And it wouldn't have been, you know, it would have been obtuse, but let's say it came out to be like 33 degrees. We would have done a lot of work to get that, right? And then we move to the next one, we get something else. It's not 90. And then we go. So at the end, we would know more about the triangle, but we could get that it's not right triangle by doing less computation. I don't know if that helps.
No, it does, yeah.
Yeah, and we'll see how the dot product later on is just going to be, we're just going to use it a lot. There's other formulas that come from the dot product, like vector projections. That's what we're going to do next class. There's the formula for projection vector. And visually, it's how we project a vector onto another vector. So we can use the dot product to actually find this vector, which is really cool if you're trying to figure out if you're pulling, let's say you're pulling on an object with a force this direction, you can actually figure out what that vector is in this direction. So you're like decomposing that vector in this direction, so you can figure out that blue, pulling on blue with a certain force is the same as pulling on purple with some other force. That's how you, in physics, you usually break it down like horizontal and vertical forces, but you can do it relative to anything. You don't have to be horizontal or vertical. Okay, I'm going beyond, but we use a dot product for that. Yeah. All right, everyone have a great day.
Thank you, sir.
Everybody signed in?